Hello, everybody. Welcome back. Today we're going to be looking at subunit 8.11, which links the concept of pH and solubility of salts. It is also the last subunit in Unit 8 on acids and bases. This has been a big one. So let's get started. So for this last subunit, I'm going to ask you to think back to Unit 7, where we covered a section on the solubility of slightly soluble salts. If you'll recall, we did lots of problems involving the equilibrium constant KSP for solubility product. And we're going to revisit a little bit of that today and talk a little bit about Q versus K and factors that affect solubility. So why is this in Unit 8? Because pH of the environment is one of those factors that can affect the solubility of a particular salt. And some salts in particular that are affected by the pH of their environment are salts that contain hydroxide. If we looked at our solubility rules, the solubility rules would tell us that this salt, iron 3 hydroxide, is either slightly soluble or insoluble. But let's think about what could the pH of the environment do to that solubility. So let's look at one situation at a time. So let's say the environment is very, very basic. And of course, by the end of this unit now, I'm hoping you understand that an environment that has a high pH means that there is a great deal of hydroxide ion floating around. Okay, well, let's think about this equilibrium system of that reaction in purple that you're seeing there. If we drop this salt into an environment where there is already quite a bit of hydroxide ion already present, that is going to cause Q to increase, because if we have this additional hydroxide, we're no longer at equilibrium. That means that Q is going to end up being greater than KSP. Let's think back to Unit 7. What does it mean if Q ends up being greater than the equilibrium constant? That means that the reaction will shift to consume product and create more reactant. Well, so what? What does that have to do with solubility? Well, think about it. If the reaction is shifting so that more of that solid reactant is being produced, that means that this salt, this iron 3 hydroxide, is not dissolving as well as it was before. The take-home message here is this particular salt, because there is extra hydroxide floating around in the environment, this salt would have decreased solubility in a high pH environment. Okay, that's also something called the common ion effect. We also saw that back in Unit 7. We've got OH minus present in this salt. We also have it present in the environment, and that's a common ion effect. We see decreased solubility. Well, what if the pH is low? Okay, maybe we're trying to dissolve this salt in a more acidic environment. Let's think back, okay, to earlier in this unit. If you have an acidic environment, that indicates that there will be lots and lots of hydronium, H3O plus, floating around. And you might say, well, hydronium's not in that equilibrium system up in purple, so it's not going to have any effect. Well, it does actually. When you have an ion that is not in that equilibrium system, there's a chance that it may in fact react with something in that equilibrium system, and in fact it does. We get this reaction happening, and actually I need to put a 2 there to balance that out. Okay, but the point is, this additional hydronium that's floating around in the environment is going to react with some of that hydroxide ion. Okay, so think about that. That's going to decrease the amount of hydroxide ion, which is going to cause, let's come back to Q versus K, that's going to cause Q to decrease, to go down, and it will end up being less than KSP. So what? Well, when Q is less than KSP, the reaction, the equilibrium system will shift to consume reactants and produce more products. So in this case, trying to dissolve iron 3 hydroxide in a more acidic environment is in fact going to increase its solubility because that additional hydronium ion that's floating around is going to react with one of the products, that hydroxide ion. Okay, so hydroxide salts are a great example of a salt that is affected by the pH of its environment. Are there other salts that could be affected? Absolutely. Let me give you another situation. Let's look at this one, okay? Calcium fluoride. And let's imagine that rather than dissolve this salt in pure water, I decide that I'm going to try to dissolve it in an acidic environment. Let's remember, what's present in high amounts in an acidic environment? That would be hydronium. Could hydronium possibly react with either one of those ion products? Absolutely. And this is what we get, okay? Now, I would expect you all at this point, being that we're at the end of Unit 8, I would expect you to be able to predict that reaction, that yes, this reaction will occur. And the reason it will occur is because we know that HF is a weak acid. Remember, weak acids will form. Weak acids are more likely to be found bonded together than in their ionized form. So this reaction will occur. Well, so what? That means that every time an F- ion is produced, it will immediately react with the hydronium in the environment. Constantly removing F- is going to cause Q, because we won't be at equilibrium anymore, to be less than KSP, which is going to cause a shift in this direction. That means, guys, that calcium fluoride is an example of a salt that is more soluble in an acidic environment than it would be in pure water. Why? Because those fluoride ions are going to react with the excess hydronium. Okay, so sometimes you'll see questions that will ask you, is this salt more or less soluble in an acidic environment? Justify your answer. If any of you are wondering, would this salt, what if it was in a basic environment? Okay, well, if you think about it, what would be present in high amounts in a basic environment? That would be OH-, right? The only thing that could possibly react with would be that calcium ion, but that's not going to happen because what could be formed, if you put those two together, is calcium hydroxide, and that's a strong base. Strong things are not going to be formed. That's a reaction that would not occur. So this salt shows increased solubility in an acidic environment only because its anion can form a weak acid like HF. Okay, so do all salts, are they all affected by the pH of their environment? The answer is no. Okay. In that statement on the previous slide, there was a statement right at the beginning, if the anion is an effective base. Well, let me show you an example where the pH of the environment would not affect. Okay, like lithium chloride, for example. So let's look at this reaction here. This is the, what lithium chloride looks like when it ionizes. Let's think about what could possibly happen if you tried to dissolve this in an acidic environment, let's say. Again, acidic environment, lots of H3O plus floating around. Which ion could it potentially react with? The chloride ion, and it would look like that. The question is, will this happen? Will this reaction happen? And the answer is no, it will not. And I'm hoping by the end of this Unit 8 here, you now know why. The reason that reaction is not going to occur is because HCl is a strong acid. Strong acids are more likely to be found in their ionized form than together. So lithium chloride would be an example of a salt that dissolves just as well in an acidic environment versus water, no difference. And again, if you're wondering, what about a basic environment? Think about it. The OH minus that's floating around in a basic environment, could that potentially link up with the lithium ion? Maybe, but again, that forms a strong base. That's not going to happen either. So this is an example of a salt that is completely unaffected by the pH of its environment. So let's look at some practice problems, okay? And again, we're looking back to Unit 7 a little bit with KSP. You can see that there's a KSP expression there. We've got the reaction for the dissolving of cadmium hydroxide, and the question says, will the molarity of the cadmium ion, just that ion, be predicted to increase or decrease with the addition of hydroxide ions? So pause the video here, see how you do with it. Okay, so first of all, guys, let's always remember we need to actually answer the question. Will the molarity of the cadmium ion increase or decrease? And I'm hoping that you said that it will decrease. And let's think about why that would be. If you have that additional hydroxide ion, the molarity of the products is going to increase. That causes Q to be greater than KSP, and we're going to get a shift in the reverse direction, consuming products, the dissolved ions, and forming more reactant, that solid cadmium hydroxide. Just keep in mind, guys, that this question was very specific to ask us about what is happening to the molarity of that cadmium ion. Since I know that the shift is going to be in the reverse direction, that product molarity should be decreasing. Okay, let's look at another question. This one's a little bit more involved. Okay, same reaction, same salt. This time it says, an experiment was performed to compare the solubility of cadmium ion in pure deionized water, that's container A on the left, and acidic water, that's the container on the right. You can see that there's extra hydroniums floating around. Which container would be predicted to have the highest molarity of cadmium ion? So pause the video, see how you do with this one. Okay, now, again, guys, is hydronium in that equilibrium reaction at the top of the slide? No, it isn't. But I'll bet you that it reacts with one of the products, and we know that it in fact does. So let's answer the question first. Which container is going to have the higher molarity? That's going to be container B. And why is that? The hydroxide coming from the cadmium hydroxide is going to react with those hydronium ions in container B. So what? Well, that's going to decrease the molarity of products. That's going to cause Q to be less than KSP, and we know, of course, if Q is less than KSP, the reaction is going to shift in the forward direction, consuming reactants, forming more products. That means an increased solubility of this salt and increased molarity of that cadmium ion. So that would be a great example of a free response question you could see dealing with this concept. Whew, okay, so that concludes Unit 8. Again, this has been a huge unit. Acid-base is a massive topic. on the AP exam. So I appreciate you sticking with me through this intense unit, and I hope you learned a little something, and I look forward to seeing you all in our last unit of AP Chemistry, Unit 9. I look forward to seeing you next time.